I would like to talk briefly about adiabatic cooling, airlifting, and precipitation, as these are three very important concepts in the study of meteorology. Adiabatic temperature change refers to the warming and cooling of air as a result of air compression and expansion. It's important to note that adiabatic temperature change does not involve actual addition or loss of heat, but rather occurs as a result of a change in air pressure. When air expands under decreased air pressure, it undergoes cooling. When air is compressed under increased air pressure, it undergoes warming. Specifically, adiabatic cooling refers to the cooling of air as it rises and expands with upwardly decreasing air pressure through the atmosphere. This occurs at different rates depending upon the air's degree of water vapor saturation. We will consider both the dry adiabatic cooling rate and the wet adiabatic cooling rate. This process results in the formation of clouds. Dry adiabatic cooling rate is related to air that is not fully saturated with water vapor. Here we see that air cools at a rate of 10 degrees Celsius per 1,000 meters. Wet adiabatic cooling rate relates to air that is fully saturated with water vapor to the point that it undergoes condensation. While the air continues to cool, it does so at a decreased rate of 5 degrees Celsius per 1,000 meters. The basic steps in the adiabatic cooling process involve a parcel of air leaving the ground and cooling at the dry adiabatic rate of 10 degrees Celsius per 1,000 meters. Once the air has cooled enough to reach its dew point, condensation occurs, releasing latent heat of condensation into the atmosphere. This released latent heat of condensation warms the surrounding air, thereby acting against the cooling rate. The parcel of air continues to cool, but at the lower wet adiabatic rate of 5 degrees Celsius per 1,000 meters in its ascent. This is a diagram showing the adiabatic cooling process and the associated rates. Here we can see the air begins at the surface, cooling under the dry adiabatic rate until it reaches its condensation level, allowing for the formation of clouds. From here, the air continues to cool, but does so at the wet adiabatic rate. Now I would like to talk about air lifting. As previously discussed, cloud formation occurs when adiabatic cooling of rising air sufficiently cools the air to its dew point. Upon reaching this level of water vapor saturation, the water vapor within the air condenses to form clouds, or in some instances, fog. However, air can be resistant to the vertical ascent that is required by this process, so important mechanisms exist that force the air to lift. There are four different air lifting mechanisms that I would like to discuss. They are orographic lifting, frontal wedging, convergence, and localized convective lifting. Orographic lifting results when there is a physical barrier to the flow of air created by elevations in the terrain such as mountains. These elevations force the air upward. Frontal wedging results from a collision between warm and cold air masses. In this collision, less dense warm air is forced to rise upward over the barrier created by the more dense cool air. Convergence results when air flows in from multiple directions. This leaves the only possible course of direction for the air as an upward path. Finally, localized convective lifting results when pockets of air are warm more than the surrounding air due to uneven heating of the Earth's surface. This creates parcels of air with a lower density called thermals. Finally, I would like to talk briefly about precipitation. Precipitation formation requires that millions of minuscule cloud droplets combine to produce a rain droplet that is large enough in size to withstand the fall to Earth's surface before it evaporates. There are two mechanisms for the formation of precipitation: the Bergeron process and the collision coalescence process. First, we'll assess the Bergeron process, sometimes called the aggregation process. In this process, ice crystals, which have a greater affinity for water vapor, collect all of the available water vapor while sacrificing supercooled liquid water droplets with which they coexist in cold clouds to evaporate. Precipitation falls as snow in the winter, or in the summer, the ice crystals or snow is able to melt and then falls as rain. Second, the collision coalescence process is characterized by larger liquid water droplets formed by hygroscopic particles such as salt in warm clouds colliding with smaller droplets as they rapidly fall. These larger droplets are able to fall at a faster rate, thereby coalescing with smaller droplets to eventually form droplets large enough to reach the Earth's surface before they undergo evaporation. The types of precipitation I would like to highlight are rain, snow, sleet, and hail. Rain is simply drops of water that fall from clouds with a diameter of at least 0.5 millimeters. Snow is ice crystals or groupings of ice crystals that fall frozen from clouds and remain frozen during their descent. Sleet actually begins as raindrops that fall from clouds, but upon passing through layers of sub-freezing air, they freeze and turn into ice particles before they reach the Earth's surface. Hail is hard, rounded, or irregularly shaped pellets of ice that are produced by high updrafts of clouds in which ice crystals and supercooled liquid water coexist. These have a diameter of approximately 1 to 5 centimeters. It's important to note that hail can only be found in unstable systems.